Okay, this video here will be the first of several videos dealing with a class of molecules called carbohydrates. This name carbohydrate comes from the fact that the molecules we're going to talk about in this chapter have the formula CN and in parentheses H2ON, hence they are hydrates of carbon, and that's where the name originates. In general, these compounds have one C double bond O group, which is usually either an aldehyde or a ketone, and it has many OH groups attached to sp3 carbon. The chemical reactivity, we've already had it before. It's a blend of the reactions of alcohol groups, C double bond O groups, and acetals. And we're not really going to introduce any new reactions. We're just going to look at reactions we've already had, but they're going to be applied to larger molecules with a lot more functional groups. Okay, let's review a few terms here. Saccharide. This is just a fancy name for a carbohydrate molecule. Sometimes another name we're going to see here is just a sugar. Okay. Monosaccharide means that the hydrolysis or the reaction with aqueous acid and heat is not going to produce any simpler compounds. Okay, a good example of a monosaccharide is glucose, which has the formula C6H12O6. We do not produce simpler carbohydrates by hydrolyzing glucose. It's as simple as it can get. Okay, all right, so a disaccharide would have two monosaccharide molecules hooked together. A good example of a disaccharide is sucrose, ordinary table sugar, which has the formula C12H22O11. If we treat this compound with H3O plus and heat, we're going to get 1 mole of glucose, as we've seen before, a monosaccharide, and another monosaccharide called fructose, and both of these have the formula C6H12O6. All right, notice that if you add C6H12O6 to another molecule, you get C12H24O12. Okay, all right, so if we do that, we have C6, C12, H24, O12. All right, so what's the difference between this formula and this formula? Right? And of course, this is minus water. Okay, so when we make a disaccharide from two monosaccharides, we're going to eliminate one water unit, and that's something we'll look at very late in this chapter. All right, so a polysaccharide is going to produce many monosaccharide units upon hydrolysis. A good example of a polysaccharide is cellulose, or we'll just call it starch. Okay, cellulose and starch are good examples of polysaccharides. When you hydrolyze either of these materials with aqueous acid and heat, if you wait long enough, you're going to get lots of glucose molecules. In between polysaccharides and disaccharides, we have trisaccharides, tetrasaccharides, and I'm just going to introduce this other term called oligosaccharides. Okay, there's no firm point over where where it transitions from an oligosaccharide to a polysaccharide, but oligosaccharide has a few monosaccharide units, the polysaccharide has many. Obviously, these are not quantitative terms, but they're in use quite extensively. Okay. All right, let's look at some structural and chirality classifications. First, let's look at structural classifications. All right, we're going to call a monosaccharide an aldose if the C double bond O is an aldehyde, and we're going to call it a ketose if the C double bond O is a ketone. We're going to further classify it by the number of carbons in the longest chain, or actually in a monosaccharide, the only chain. Okay, and we're going to use the Greek prefix for the number of carbons and end it with the word os. Okay, our preferred depiction for a monosaccharide is a Fischer projection with the C double bond O as close to the top as you can get it. Okay, and the carbon chain going perfectly vertical. Okay, and these are going to be further classified by chirality terms. Okay, let's just take these 4 compounds here and classify them. All right, if we look at the first one, there's 3 carbons in our chain there. This one, 1, 2, 3, 4, 5. There's 5 carbons. And these last 2 each have 6 carbons. 1, 2, 3, 4, 5, 6. All right, so the first one's going to be a triose of some sort. The second one is going to be a pentose, and the last 2 are going to be hexoses. All right, so the one on the left is an aldehyde. This is called an aldotriose. The molecule that I've drawn here is D-glyceraldehyde. The molecule here is an aldopentose, and the molecule that I've drawn is called D-ribose. This third one here, also an aldehyde, but with 6 carbons, is an aldohexose, and this one is D-glucose. All right, and this last one over here, the carbonyl compound, is a ketone and not an aldehyde. So this is a ketohexose, and this is fructose. All right, we're going to further classify carbohydrates by chirality terms. And let's just review a few of these chirality terms, since it's been a long time since chirality was really an important issue. Okay, we've been dealing with relatively, or actually, flat functional groups for a long time. So let's just review a few of those, and I'm going to kind of narrow it down to the definition that works best for us. Okay, so an enantiomer technically is a non-superimposable mirror image isomer, but in carbohydrates we're going to look at them as being compounds that differ in the configuration at every chiral center. Okay, and they're going to be distinguished by a D versus L in the front of the name. Okay, we'll look at what that means on the next slide. A diastereomer, and for carbohydrates the definition that works best is that they are different at least one, but not all of the chiral centers. 2 monosaccharides that are diastereomers will have different names. This is an important point. If they're diastereomers, they're going to have different names. If they're enantiomers, they're going to have the same name, but the D or L that's in front of the name is going to be the only difference. An epimer is a diastereomer that differs at only one chiral center. A meso compound, we're going to encounter these later in this chapter after we do some reactions, but it's a compound that has chiral centers, but it's not chiral because there's a plane of symmetry somewhere. And a Fischer projection. This is our preferred way to present these molecules. And remember that in the Fischer projection, the vertical lines go back and the horizontal lines come out. Okay, with carbohydrates, they're a little bit more complicated because in most cases we have more than one chiral center. Okay, the standard convention is to draw the C double bond O as close to the top as possible and have the backbone, the carbon backbone or carbon chain go straight down from that point. Okay. All right, this is an important point because if we draw all of our molecules the same way, we will find it very easy to understand just by looking at the Fischer projection or looking at the cyclic structures that we're going to see later, that we can very easily distinguish the chirality issues without ever assigning an R and S configuration. Okay? All right, so many of you may have bad memories of the chirality chapter, but what's going to make it a lot easier in this place is there's kind of a universal agreement amongst all organic chemists to draw all of their carbohydrate molecules from the same perspective. And because of that, these chirality issues are much easier to understand in these molecules. Okay, so let's look at this, the D versus L configuration. It all arises from one compound, glyceraldehyde. Okay? This is the enantiomer of glyceraldehyde, the one shown here on the left that has the positive specific rotation value. And we're going to call that one the D for dextrorotatory, and it happens to also have the R configuration. Okay. The enantiomer of glyceraldehyde has a negative specific rotation, and we're going to call that the levorotatory, or left side rotation, and this has the S configuration. Okay, every chiral center, every larger carbohydrate originates from this simple molecule here, glyceraldehyde. Okay, it's the observations in glyceraldehyde that define D and L for the structural, or for the higher carbohydrates. Notice that this is capital D and capital L. It's not meant to imply the rotation. It turns out that it's a wonderful coincidence that almost all of the D sugars do have a positive specific rotation, but it's important to remember that this is a structural feature. It's not a specific rotation feature. It is a wonderful coincidence that in most cases it is this way, but the capital D versus L is a structural term. Okay, for carbohydrates larger than glyceraldehyde, we're going to call it D if the OH group at the bottom, that's the one that has the highest IU number according to the IUPAC system. If this chiral center, if the OH group at this chiral center goes to the right, it's the D enantiomer. And if the chiral center at this carbon goes to the left, it's the L enantiomer. Okay, so here is D-erythrose right here on the left, okay? If we want to think of what does L-erythrose look like, we have to make sure that the bottom chiral center is going to the left, and we have to make sure that every chiral center in D-erythrose is opposite to every chiral center in L-erythrose. They have to be completely opposite. They have to be mirror images, okay? All right. Okay, so these are enantiomers. Notice that they're both called erythrose. The only difference is that one is D, one is L, and we get the D versus L by looking at the picture, okay, by looking at the Fisher projection. Okay, a diastereomer of erythrose would have one chiral center the same and one of them different, and this compound is called threose. Okay, so this is the diastereomer of erythrose. Okay, and note here that this is D-erythrose, this bottom chiral center here. The OH group is going to the right, and up here this other one goes to the left, but this is the one down here that defines D versus L. Okay, this is the bottom one right here. Okay, if we want to draw L-erythrose, we have to have the opposite stereochemistry at every chiral center, and we have to make sure that the bottom chiral center, the one here, the OH goes to the left. Okay, so this is L-threose. The bottom one goes to the left, and the top one goes to the right. Most important is that it's the opposite. Every chiral center in L-threose has to be opposite to every chiral center in D-threose. Okay, all right. Notice that all the compounds that have different names are diastereomers. Okay, so D3-ose and L3-ose are both diastereomers of D-erythrose. And that if two compounds are enantiomers, the only difference is the D or the L in front of the name. Okay, let's review an important chirality term from the past. Notice that with glyceraldehyde, we only had a D and an L. With erythrose, an aldotetrose, with two chiral centers, we had 4 different compounds. It's important to remember this important relationship, or this important equation from the chirality chapter. The number of possible diastereomers, or number of possible stereoisomers, equals 2 to the n. That's the maximum number of stereoisomers. Okay, so of these 2 to the n, there will be 2 to the n minus 1 diastereomers, and each of those diastereomers are going to be a pair of enantiomers with a D or an L in front of their name. Okay. All right, so there are 4 D-aldopentoses. This is when we put one more chiral center here. And if we put an additional chiral center, have an aldohexose, there are 8 possible aldohexoses. Okay, so 4 new names for the aldopentoses and 8 new names for the aldohexoses. All right, so let's do a little exercise here. If given the structure of D-glucose, you should be able to draw the structure of L-glucose. And knowing that D-mannose is merely the C2 epimer of glucose, we should be able to draw D-mannose, knowing the structure of D-glucose. All right, so what is the structure of L-glucose? We have to take every chiral center in D-glucose and switch them. Okay, if you're actually using the program I use, ChemDraw, all you got to do is type Control-H. Okay, but you're going to have to do this on a piece of paper. All right, so this is L-glucose here. Every chiral center is opposite to what it is in D-glucose, and notice that this bottom chiral center right here, the OH goes to the left. All right, what's the number one mistake that students make when asked to do something like this? They'll turn around the bottom chiral center and leave the rest of them the same. Don't do that. Remember, an enantiomer is defined as a mirror image isomer, and you got to have every one of those chiral centers opposite if they're enantiomers. Again, you know they're enantiomers because the only difference is the D versus the L in front of the name. Okay, D-mannose is the C2 epimer of glucose. Let's do the IUPAC numbering system. The aldehyde should be carbon 1. That should be 2, 3, 4, 5, and 6. All right, so we're going to focus on carbon 2, and we're just going to invert that stereocenter right there. That should be D-mannose, and there is D-mannose right there. Okay, the only difference is the configuration at carbon 2. All the other carbons are the same as glucose. So we say that it's the C2 epimer. Okay, so the way this chapter works is we slowly introduce a little minor complication that's going to make our life a little more difficult, but then we're going to deal with it, and that's what's going to happen in the next video. We're going to look at how these, notice that the compounds have an OH group and a carbonyl group. You may remember back in the ketone chapter that there's an equilibrium with hemiacetal, so that's going to be the next topic. Okay?